Hi, everyone. Good afternoon for everybody, or good morning for some people. It's really a great pleasure to have you in our webinar. We have a lot of people today. We have close to 200 registrations. So it's clearly that this topic is of interest to people, advanced treatment in general. And yeah, it's nice to have you with us. The Amazon webinar series, we are now doing it for several years, has become quite popular. And it's really great to see you back, many of you. And we also have a couple of new people here. So all of the other Amazon webinars from the past are available on our YouTube channel, so feel free to check it out. This webinar here is about preparing for micropollutant removal, or if we go to the US, they call it trace organic contaminants, or we sometimes call them emerging contaminants. So they have a lot of terminologies. But it's about smart planning, design, and operation, because a lot of utilities or end users are currently taking steps in that direction, or they are considering advanced treatments. And that makes this webinar super exciting. I am Wim Oudenaard. I'm CEO and co-founder at AM Team. And I have the pleasure of being the host today and introducing this webinar. Now, the introduction of this webinar will be super short because we will have to go to our guest speaker pretty soon in a couple of slides. Because Peter, our guest speakers, will need to leave actually in time. So he will need to leave in about 25 minutes. So this means we will start with Peter. So this means this is a quick webinar intro. We will start with that. Then Peter will straight jump in. He will straight jump into the story of Waterschap De Dommel, Waterschap De Dommel, a Dutch utility. And they will talk about their 10 years journey and on tertiary treatment and how models can be useful there and how they used models. And Roberta, our colleague, will then be continuing, and she will be zooming in on the planning and the design stage and give a couple of more insights there related to the case. And I will end then with the global application of Amazon and how can you actually use Amazon and work with us. So this is also quite an important section if you look at the application of it. This webinar will have some polls coming to you. You will see one straight after the slide, I think. And also, if you have questions, we highly recommend actually to ask a lot of questions. Please use the Q&A window, okay? Not the chat, use the Q&A window. All right, quickly, for people that are not familiar with Amazon, one slide in order to understand Peter's presentation. Amazon is a globally unique engineering and digital twin model for ozonation and advanced oxidation. It is being used in the piloting stage or the planning stage, which we call virtual piloting. Okay, you use a model to do technology assessments in the planning stage or technology feasibility testing. It is also being used in the design stage for conceptual and detailed design. Peter will also talk about this. And it is also being recycled or used as a digital twin model. We will quickly touch upon that because that's ongoing work, but it's also a very important application area. Okay, so these are the applications of Amazon. We started building this model solution in 2017. So quite a couple of years ago already. It has a combination of benefits. I will come back to that, and you will see it throughout the webinar. And also, it has been applied at over 50 plants already. It impacted 50 full-scale designs or operation of plants. So 50-50 drinking water, wastewater, or reuse, okay? Quick, because again, we don't have a lot of time. We will start with a first poll. It's a first poll to just know who is in this webinar, okay? Which type of organization do you work for? Is it consulting and engineering? Is it water utility, industrial end user, technology vendor, or research institute or researcher, or other? So votes are coming in. More than half of you, 60% have participated. We are going to 70%. I will give it like 2-3 more seconds. All right, interesting. And the poll, I will also show the results, okay? Then you can also see it. The majority of you, it's close to 40% is water utility, and that's great. And we knew that because in Europe, there's so much happening here. We have a lot of countries, a lot of utilities from different countries represented in this webinar. Super cool. And then, of course, who is working a lot at the application side is consulting and engineering. There's really plenty of work to do. And we will also come back to that. And of course, technology vendors are very active in the area. and a lot of research is being done as well. So thank you for voting. And now I actually will give the floor to Peter already to not consume too much time. So Peter will be sharing his screen and be introducing the journey. So Peter, the floor is yours.
Thanks for your introduction. Hi everyone. I am Peter van Horne, and today I have the pleasure of talking about our journey with tertiary treatment at Waterschap De Dommel. We are a Dutch water authority that manages the water in the central part of the province of Brabant. I will start with explaining our journey on the removal of micropollutants that is already going on for over 10 years. As this is a webinar focused on the application of modeling in tertiary treatment, I will then zoom in on how we applied modeling in planning and design stages, and how we plan to use it in the operational stage as well. I will conclude with some key lessons and future perspectives. We already started working on the topic of micropollutants over 10 years ago. It all started with an original initiative in the River Meuse Basin, de Schone Maaswaterketen, a collective between local water authorities, drinking water companies, the Dutch Ministry and Rijkswaterstaat that wanted to safeguard the Meuse River from micropollutants. You can see the goals on the right. If we would do nothing, the micropollutant concentrations would increase with 1% a year. Instead, the goals are to reduce the micropollutant concentrations with 20% by 2027 and with 30% by 2040. Substances of concern are even of higher priority. In 2015, under this initiative, first pilots were initiated with powdered activated carbon. Also, a regional hotspot analysis was conducted to define the priorities. As a result of this hotspot analysis, 5 of our treatment plants were identified as hotspots. You can see these wastewater treatment plants on this slide with their respective capacities. The first plan was to use PACAs for our biggest plants, Eindhoven and Tilburg, to be operational before 2023. In 2020, concrete plans were being made towards full-scale implementation. In order to learn, we then started detailed investigation at our smallest plants, Hapert and Soerendook. In 2020, feasibility testing was performed for GAC at Hapert and Ozone at Soerendook. Shortly thereafter, a GAC upflow pilot was installed at Hapert and operated for 1.5 years. At Soerendook, we wanted to test the feasibility for ozone treatment. We decided to take a new approach, a virtual pilot with the AMOZONE model of AM team. I will explain some main reasons later. While conducting the virtual piloting at Soerendook, we also decided to extend the virtual piloting to Hapert and Eindhoven. We hence conducted virtual piloting at 3 of our plants. As I mentioned before, we started working on micropollutants before any European regulation or national subsidy programs were implemented. In 2019, STOA started an innovation program on micropollutants removal to conduct research on feasibility of different techniques. To accelerate full-scale implementation of tertiary treatment, the Dutch Ministry launched a subsidy program called Bijdrageregeling, and we had the chance to apply with the Hapert pilot. The figure on the right shows all of the first large-scale initiatives in the Netherlands that were included in the first batch of this subsidy program. On the left, you can see ozone applications, and on the right, you can see PAC applications. We needed to continuously navigate a changing landscape. For example, initially, we were looking at an indicator micropollutants list of 19 components, while in the end, we ended up with a final list of 11 indicator components. The 70% removal of these components is the key KPI to meet in this national program. The biggest change for us was the discussion on bromate. In 2022, the Netherlands decided the most stringent bromate limit in the world. The effluent of an ozonation plant should not exceed 1 microgram per liter. As we already had ongoing initiatives, we needed to address this change. This provided some context on where we came from. I will now zoom in on the first application of AMOZONE, virtual piloting in the planning stage, to conduct technology feasibility testing. Some key reasons why we chose for the approach of virtual piloting are on this slide. We were quite tight on time and had limited experience with ozonation, which was posing a risk. Also, at the national level, there was limited experience back then. A real piloting comes with some staff and operational challenges. Also, in this changing landscape, we were in need of testing flexibility. A fixed pilot with a finite duration would have been valuable for that time, but just imagine you would like to run more scenarios or tests later on. With the model, we could do this. I already discussed some of these changes that required flexibility. In addition, we were in need of testing specific flow scenarios, and later on, bromate suppression strategy testing became very important. The virtual piloting also allowed us to screen multiple plants at a time. We also considered future applications of the model. The model, once built, helped in staff training. Most of the staff training had no experience with ozonation. And finally, the digital twin application for future advanced monitoring and control was considered an important asset, certainly given the stringent bromate requirements. In this slide, you can see the 3 plants we considered for virtual piloting, together with the bromide levels. Bromide levels are important, as the higher the bromide, the higher the risk for bromate. You can see that Surendonk potentially has the highest risk. The virtual pilot was set up using real plant data and sampling. We took several effluent samples at our plants, and the AM team sent those to a dedicated lab in Germany for ozone batch testing. These tests were used to screen the unique fingerprint of each effluent matrix. In the lab next to ozone demand, also the bromate response was being assessed. This information was crucial to calibrate the virtual pilot model for each plant. In addition to that, in exchange with the AM team, we installed a temporary scan UV spectral sensor at each of those plants to get a view on the dynamics of DOC. As this is a variable we typically do not measure. However, DOC is important for ozone demand. Also, AM team used existing online and offline plant data from each of the plants, for example, the flow rates and ammonia. I'm not going into details of the outcomes, as AM team will dive a bit deeper later in this webinar. However, I wanted to show you some key results from that virtual piloting that supported our decision process. On the left-hand side, you can see predicted removals of the 11 micropollutants. Each of the groups is a different ozone control strategy. The virtual pilot was used to test different ozone doses, control strategies, and later on also bromate suppression strategies. The dynamics of the plant were used. On the right-hand side, you can see the predicted dynamic bromate profile at the Haber plant for one of the scenarios. Typically, these dynamics are invisible as we are used to take grab samples of bromate. This provided us insights on what drives the bromate formation. For example, effluent ammonia contributes to bromate suppression. The virtual piloting scenarios, supported by the lab-scale ozonation experiments, provided us with sufficient confidence on the feasibility to remove micropollutants while keeping bromate sufficiently low. As a final result of our feasibility assessment, we decided to proceed with the full-scale design at 2 plants, Hapert and Soerendonk, based on cost and carbon footprint assessment. Ozone as a standalone was chosen at Hapert. Now we are considering combined treatment of ozone and GAC, but I will come back to this later. Unfortunately, in the detailed design stage, the cost became higher than expected, also partially caused by COVID. We needed to make the difficult decision to put Soerendonk on hold. We hence proceeded with the design and construction of Hapert. Oh. Sorry about the late color change topics. I will now zoom in on the design and commissioning of Hapert, which has become our first full-scale tertiary treatment facility. We have chosen for a bow-team approach, which is more and more used in the Netherlands. While our request was conceptually formulated, the market request was not overly detailed to allow flexibility during the project. A consortium of complementary parties worked together to then shape the final outcome. CLC Water, a consortium consisting of ADS Groep, Nijhuis, Witteveen en Bos, Moekotte, and Pannenkoek, was chosen to design and construct our first full-scale facility. As you can see, we also brought in AM team as they had conducted the virtual piloting and could now upcycle the model into a detailed design model. AM team, CLC Water and us worked closely together in this project. The model from the virtual piloting stage was a dynamic model that was used to assess the impact of plant dynamics on micropollutants removal and bromate formation, as you have seen before. In this stage, AM team converted the virtual piloting model into a 3D design model by adding computational fluid dynamics. This model allowed us and the consortium to conduct what-if testing on the detailed design. For example, we tested flow rate variations, bevel design, gas introduction strategies, and peroxide dosing. Without going into detail, this table gives you an overview of different scenarios we have run throughout the design stage. The outcomes were discussed with the consortium and new scenarios were determined and tested. A really innovative aspect here was that we considered a co-current configuration, while typically a counter-current configuration is being used. In this configuration, the ozone gas and the water flow in the same direction. On this slide, you can see a comparison of both co-current and counter-current design, as shown with the top graphs. According to the model, lower dissolved ozone concentrations are expected in the reactor, even if the same ozone dose is being added. Less ozone residual is expected to lead to less bromate formation, as shown at the bottom. In the counter-current design, a bromate hotspot is expected, especially in the second compartment, where ozone demand was lower, as shown by the red colors. Based on the model, a bromate reduction of about 40% is expected when co-current is combined with a smart distribution of the diffusers. This is significant. The model indicated that due to the rapid consumption of secondary effluent, the ozone mass transfer would still be fine. In drinking water, this can be very different, but counter-current is common practice. For us, the consortium and also other utilities in the Dutch market, the findings on co-current, spreading the ozone dose, and the ability to suppress bromate with peroxide were important. I can show you some very first results of our startup for the ozone installation. Unfortunately, we were struggling a bit in startup phase and had delays in commissioning. That's why there are still limited results. However, on this slide, you can see the first results of micropollutant removals for the 11 target components. AM team has already run the available model and compared it with these initial measurements. The measured data are the orange bars, while the model predictions are the blue bars. The difference of removals for individual components are clearly visible and are quite well captured by the model. The model was not yet recalibrated based on this data. We still need to start assessing bromate formation. However, the first measurements we have done before the final discharge were below the detection limit. The off-gas measurements also show a good ozone transfer, which is important for process efficiency. This brings us to the conclusions of this presentation. As you could see, we are working on micropollutants for over 10 years and had to navigate a changing landscape. We have explored various technologies such as PAC, upflow, GAC, and ozone. The bromate regulation in the Netherlands was one of the key concerns in our application of ozone. We have relied on AM team's AMOZONE solution in the various stages of our journey. It started with the planning stage, in which virtual piloting was being applied at 3 of our sites. Each of those sites was indicated as suitable for ozonation. For our first full-scale plant Hapert, the AMOZONE CFD combination was used as a detailed design model to integrate minimal bromate by design. In collaboration with the consortium, we believe we have come to an innovative treatment concept. Key findings were how the ozone is introduced and how bromate can be suppressed if needed. At this moment in time, we are commissioning the plant and first results are coming in. Early indications are very positive. Once stable in operation, we will work with AM team to implement the AMOZONE digital twin. In that stage, the model will perform real-time prediction of bromate and micropollutant removal. Another important development is an ongoing European Interreg project with Dutch and Flemish partners. We are going to run a real combined ozone and GAC pilot at our Tilburg plant. Tilburg was taken as a priority due to stringent European effluent requirements. Given the tight bromate requirements and flexibility of combined treatment to remove a broad spectrum of micropollutants, we are actively pursuing ozone plus GAC. In parallel with the on-site demonstration testing, we will run the virtual piloting with the AM team to expand testing freedom. And the AM team is working on extending AMOZONE with an absorption model in this project. And then rest to me to thank you for your attention. Thanks a lot.
Yeah, Peter, thanks so much for your presentation. Was a nice story to bring. It's years of work that has been summarized in a presentation, so quite challenging to bring in 20 minutes.
It is.
I think you will have to leave, right, Peter? Now, I guess.
Yeah. I'm
All
sorry
right.
to leave, but
Yes.
if there are any questions remain, let me know.
Yes. We will for sure pause them on, and for sure. So, Peter, you are free to go. We thank you very much for this very interesting collaboration, of course, for many years already. We are working together, but also for presenting here.
You're welcome. Thanks for your cooperation as well.
Thank you, Peter. All right. Good. So while Peter is leaving, we will continue this webinar, and I will try to share my screen again. Let's see if this works. So Roberta, can you actually let me know if you see my screen moving?
Yes, that works.
Now you see it? All right,
Yeah.
because I was informed by our team that actually you didn't see the first slides I presented. So I will just quickly walk you through. I will not repeat them, but I showed the title slide. I showed the introduction. So actually we had this story here where Peter presented the journey of the Dommel. Then we will have Roberta shortly come. So she will come after these slides I'm going to show now. And then I'm going to end with the global application of Amazon. I just wanted to show you again the table of contents so you don't lose track of this webinar, okay? This was the cycle I have shown on the applications of Amazon and Peter. Okay, all right, we are back on track. You see my screen correctly, and we will just continue with one more poll, which is on the stage, okay? In which stage or stages are you active? Are you working on technology development? So are you really a technology developer vendor? Are you working on strategy and planning? So you are in consideration stage, for example, of advanced treatments. You're designing or redesigning existing facilities, or you really are in operations. You can also have multiple answers, because I realize many of you or multiple of you will be active in multiple of these domains. All right, so we have half of you that participated. We are at 60%. Let's go to 70. Almost at 70. This is also a good signal that people are paying attention, that you're not sleeping. This is always why we do the polls during a webinar, huh? to as a as a check. I will share the results with you. Great. So most of you, that's very interesting. So more than half of you are actually in the design or redesign of existing facilities. Many of you are also in strategy and planning, and also in the development of technologies. So the minority, let's say 20%, is in the design of or the operations of existing facilities. There are also other stages, apparently, so we will need to capture them in the next polls. So thanks for voting. This is super interesting to know. All right, I will. So I'm going to stimulate people to ask questions. So just a reminder that we have a Q&A. If you hover over the screen, you can ask your questions. So feel free to ask questions. In the coming slides, you will be seeing from Roberta. This will be a very good moment to initiate the discussion and ask a couple of questions. Okay, you can do it anonymously or not. You can choose. Good. I didn't have the time to introduce ourselves properly. So that's what I'm going to do now, and thereafter I'm going to give the floor to my colleague. So I'm Wim Oudenaert. As I said, I'm co-founder and CEO at AM Team. And we also have in this webinar Giacomo Bellandi. He's our technology lead, works a lot on these models. Have been working on Amazon actually for since the start of her business. And then we also have Roberta, she is senior advanced modeling engineer and also project manager at AM Team. So Roberta will now continue on the story of Peter. Peter has brought it in a summarizing way, so this means he's not going into the details, but Roberta will now show more depth, let's say, and further applications, okay? She will start with the planning stage, and where she will highlight again the virtual piloting applications, which is, by the way, actually really emerging. It's really rapidly emerging. So Roberta, the floor is yours.
Right, thanks, Wim. So indeed, I will go a bit deeper in the application of the Amazon model in the planning stage and in the design stage. So starting with the planning stage, the Amazon model is currently being used as a virtual pilot, so in a virtual piloting stage, to assess performance and also give a preliminary estimation of the costs, for example. So to continue on Peter's story, we are now comparing the three type of water from Eindhoven, Hapert, and Surendong, so the three wastewater treatment plants that Peter already mentioned, in terms of water matrix. The bromide has been already discussed before by Peter, so we know that Surendong has the highest risk in terms of bromide formation due to the higher bromide concentration, so I won't go in deeper in that. But also another way to look at it, to look at the effect of the water matrix on the overall performance, is to look at the costs. So a preliminary cost estimation of the capital cost and the operational cost of the installation is being shown here in this slide, and the capital costs that these are mainly driven by the size of the installation. So the bigger the size, the more cost effective it is. While on the OPEX, so the operational cost, the water matrix is also an important factor there and can influence the operational costs in the end. And what we saw in these three cases, so particularly in Eindhoven, that water matrix is less loaded with organics. So the ozone consumption was a bit slower and was a less ozone demand compared to Surendong and Hapert. And this led to a slight reduction of the operational cost. So that's how at first a preliminary estimation that we could on the OPEX that we could do with the virtual piloting using the AMOZONE model. Another type of application is in combination with the real piloting. Quite often we combine both, so the real data from real piloting and virtual piloting so outcomes from the model. The real piloting is needed because it can, of course, it's needed for the calibration of the model, validation of the model, but also some fine-tuning and refinement of the model of certain assumptions. But also the model, so the virtual piloting can be used to, for example, enhance or expand the data. In this slide, we're showing two examples. On the left is a data enhancement example. So you see a comparison between model bromate production in the real experimental setup compared to the experimental setup, so compared to the real actual data in orange. So as you can see, sometimes the experimental data can be unreliable, or there are some missing data or certain failure in the measurements. And in the model, we can with the model we can fill these gaps and provide the outcomes, what would be the output of the installation. Another example is to expand the type of variables we can look at. Here we're presenting an example on a micropollutant. So typically only few micropollutants can be measured, and sometimes most of them are not detectable or cannot be measured. So with the model, we can include those extra micropollutants and also evaluate the removal of those. So the model can predict what cannot be measured or that is below the detection limit. But this is for micropollutants in this example, but can be also when it comes to disinfection in drinking water, for example, when we want to evaluate the disinfection on bacteria or viruses. Another example of a virtual piloting application is when we want to make the link from piloting or lab scale to a full-scale implementation. That's also quite a challenge very often. In the experimental setup, there is also a challenge, or there is not complete flexibility or freedom to test different things, to test different water matrix composition or different operating conditions. So there is a limitation in the testing flexibility. With the model, we can run hundreds of simulations that can go even beyond the experimental setup or the experimental operating range, And we can look at what would be the best or the optimal operating range, the optimal ozone to DC ratio, for example, in order to stay within the bromate limit, and at the same time meeting the removal, the target removal of the micropollutant. So we can help making this link from the lab scale implementation or the pilot scale implementation to the full scale implementation. The second application that, of the AMOZONE model that we wanted to bring today is in the design stage. So it can be used as a virtual process design. And this is exactly what we tested, what we implemented in the Happert case that Peter shown. So there we started from an original design concept. We, with the CFD AMOZONE model, we could highlight some certain deficiency in the design, in that original design implementation. And with the model, we have lots of flexibility to test many things, to change the design, switching chambers or placing different placement of the diffusers or changing the baffle, etc. So we have ample flexibility. And finally, we could converge in this final design concept with the co-current configuration. And why we went for this co-current configuration? That's from the hydrodynamics impact on the kinetics, on the ozonation reaction. In particular, in the countercurrent configurations, we could always see this kind of behavior in the hydrodynamics, so this strong recirculation that happens in the ozonation chambers, and a preferential stream or a shortcut towards the outlet of the chamber, which means that in certain location, the water stays longer in the system than it should be, while in other location, the water stays shorter. So there is a shortcut. And what happens to the kinetics is that the ozone dose cannot be delivered uniformly. So there is not even distribution of the ozone dose in the chambers. And this effect could be minimized with the co-current configuration. So having the gas and the liquid flowing in the same direction upwards, this was able to minimize the effect, this recirculation, and reduce the shortcut. And the ozone dose could be delivered more uniformly. Of course, there was a certain concern in this kind of design concept because that was the very first implementation. So the Happert case is the very first implementation worldwide of this co-current configuration concept. And there was a certain concern when it comes to mass transfer efficiency. From the model, we could see that it could work. So the mass transfer efficiency was above 95% in all the scenarios tested, but still that was a concern. And the full-scale plant is actually being operated since February. And they are also measuring the mass transfer efficiency, as you can see in this slide. So this is measured mass transfer efficiency that is always above 98%. So that's a confirmation that this type of design concept can work in secondary effluent water, different topic in drinking water. Another interesting thing that we could do, it's about bromate suppression strategy with hydrogen peroxide. So we could test different dosing strategy of the hydrogen peroxide, and in particular, the original idea was to dose the peroxide in front of the critical zones, so in front of the diffusers, where you have the highest peak, the highest concentration of ozone. And ideally, this would have the biggest impact, the highest impact on the suppression of bromate. But actually, from the CFD, we could see that the hydrogen peroxide via this nozzle injection in front of the diffuser the dose could not be delivered as efficient as we wanted. And in fact, the hydrogen peroxide was pushed away from the diffusers. So in the end, the inlet injection, so before the ozone contactor, was still decided were still the most effective in the suppression of bromate. Now, so we are using currently the model to predict the bromate levels after the initial commissioning, and we used real plant data as an input to the model. So these are the predicted bromate levels even before the actual measurement of bromate comes in. So this is a 2 months period of predicted bromate in the Hapert full. So is always well below the target of 1 micrograms per liter.
All right. Thanks so much, Roberta, for your presentation. We have some questions coming in. So a question is this question is maybe for Giacomo. Giacomo, because you are working on this preliminary data. So how did you have you seen the question yourself? How did you manage? Okay, how it's about the mass transfer efficiency in real time of ozone.
Yeah. How did we manage to measure this? So it is a closed system, the headspace of the reactor, and there are sensor placed there, so we could close the mass balance, knowing the inlet and outlet ozone concentrations and the gas flow. That's how we could calculate it online. There are online sensors there.
Yeah, I suppose Dommel, of course, Peter left, but they will, of course, cross-validate, I guess, as well, with some, because all these sensors are now being, commissioned, let's say, all these measurements.
Yes, correct. Yeah. So what we showed in the slides were the calculated from their measurements that they had available so far. Yeah.
And then it's more, more scientific question. How does it work? Hydrogen peroxide suppressing bromates. What is the mechanism behind? If you can say something about that, Giacomo, as well, briefly.
Yeah, sure. Indeed, it's a complex net of reactions, but in a nutshell, what happens is that peroxide reacts with ozone, reduces the local ozone concentration and the availability for ozone to react with the bromide ion, produces extra radicals, and basically the less availability of ozone makes it more difficult, less likely to happen to form bromate. That's in a nutshell.
Yeah. All right. If I can add one more thing, Giacomo, because I did my PhD on this topic over 10 years
You should
ago.
go ahead.
I still know something about ozone. Also an important mechanism is, of course, to go to bromate, you have some intermediates. You don't go from bromide to bromate in one step, you have several steps. And some of these intermediates are being destroyed by peroxide. So this means this reaction is always going back, while actually to have bromate, you should push it forward. So that's also an impact. So it's multiple effects. Okay. So I would say keep the questions coming. It's very good that we are now initiating the discussion. We will now launch a third poll. What are your biggest worries or concerns or focus areas at this very moment in time? Is it byproduct control, for example, bromates, or is it costs, or is it process performance, for example, disinfection, oxidation? Or is it really all about technology selection / strategy / planning? What are your, again, here you can give multiple answers because it makes sense. All right, so the votes are coming in. All right, we are 50%. We are now going to 60% of you that have voted. Yes, I will now end the poll and show the results with you. So right now, and that's good, we have well selected this webinar, I think, is really on technology selection, strategy, and planning. And this is this was the virtual piloting story Peter and Roberta have been talking about, but also people are working on cost optimization and byproducts. The byproducts can be very country specific or region specific. It's great, it's incredible. For example, we know in Sweden, you have some coastal areas, high bromate risk. Some regions in Germany have are worried about bromate, while others have less worries. And then you have the Netherlands, which has a national limit of 1 microgram. So it's really diverse, the reasons of byproduct formation risk or the worries around that. Okay, so thank you for voting. We will now go to the final section of this webinar, and of course, then we will still have some time to continue the Q&A. So if you have any questions, yeah, feel free to ask them, and some are coming in already. All right, this is also a very important area okay, you might say, okay, this model is coming from somewhere. These guys are doing this for a couple of years. What are now the application areas, and how do you actually use it in practice? I will start with AM team first, because I didn't have the time in the beginning of the webinar to properly introduce us for the people that do not know us. We are actually, we are providing two things: modeling and data services and digital twin solutions. We do that for the treatment side of drinking water, wastewater, and reuse. This means advanced oxidation or ozone is a part of it, but we actually work at the full plant. So this webinar is focusing on one technology, while actually we also focus on the full plant. We are headquartered in Belgium. We have customers all over the globe. You see a couple of the customers on this slide, or the partners. And we're using the services in planning, design, and operations. And the digital twin solutions, of course, are more being done in the operational stage or in the virtual piloting stage and planning. Okay, and we provide these solutions for the utilities, the end users, technology vendors, and also consultants. The solution itself is science-based, so this model has a lot of science or chemistry behind it. You see some things here on this slide, some of the equations or mechanisms, but it really contains a huge amount of chemistry. And then you have seen that Peter explains that we do fingerprinting, because if there's one challenge we all have when you talk about advanced treatment, it is the matrix, the water matrix. Every plant, also drinking water plant, is different. And if you don't account for it, yeah, you cannot really properly design and operate. So this is the core driver for this model, but this also means you need to have this chemistry inside. This model has two forms. You actually have seen the two forms. The first form is a dynamic digital twin model. This predicts things like a micropollutant, like bromate, as function of time, as function of dynamics of a real plant. Okay, so it's a time model, while actually the other form, you have seen it, is a 3D CFD AMOZONE model. It's the same model, but in this case, it has been integrated into a 3D model. And then you have these fancy graphs. You have seen them on Peter's slides that provide the 3D insights, and they are very good, of course, for design. So each of those models have very different applications, but they are very complementary. And you have seen that we started with a dynamic model in the virtual piloting stage, then we went to a 3D model in the design stage, and now we are going back to a dynamic model in the digital twin stage at Hapert. All right, the application areas, and this is relevant for all of you because we know this audience quite diverse. We have people from wastewater, but also drinking water, and people that work across fields, also reuse. It has been used in all of it, so wastewater, and this means the treatment and the reuse. Municipal, industrial, we are working on drinking water a lot. Like I mentioned, 50% of our AMOZONE work historically has been drinking water. We are also doing a lot of greenfields, retrofitting or design work in that area, and process water as well. That's a very big area. So we are continuously extending it, this specific solution, ozone, ozone AOP, peroxide, UV, UV peroxides. And now Peter mentioned this in this project. We are actively working on as well extending it with a granular activated carbon, BGAC, a powder activated carbon, so adsorption. Because what we see is both in reuse and final discharge in Europe, the reuse is more US, let's say, yeah? The gold standard there as well as becoming ozone and granular activated carbon. So this is very important to have this. And again, look at Netherlands when you have a bromate, very tight bromate issue, and you also want flexibility in removing micropollutants, this combination is quite promising. Also in terms of carbon footprint and operation for the long term. So then as well, what you have seen is one single reactor in the story of Peter, but actually we do both unit process level, but also plant level, because if you consider plant-wide optimization, this is such a great area for the future. One example, nitrite has a huge impact on ozonation. Nitrite comes from the biology. Ammonia has a big impact on bromates. Or what if you would use the pure oxygen upstream in your biology, the off gas? So such concepts can be really, really well assessed with a plant-wide model. And again, we are doing these things. Our business model is configured as such that we do modeling services, long-term and short-term, and it also includes a lot of training. For example, the Hapert design, that's a very good example of such a service in a consortium or with a utility. And then we have digital twin solutions. You will see this word a lot. I am sure you see it already a lot. We develop digital twins, and this makes us very unique. There are not so many parties that really develop digital twin models and digital twins. And we have another business model there, which is model as a service. This means our models plug into existing platforms. And this comes with a license agreement. For example, we are using Sumo quite often as a very good simulator for AMOZONE. But for example, in the SCADA system of some clients, we have to work with solutions. So this is another business model, the digital twin solution. And what I really want to stress is that we are trying to fill a void in the markets because we have a lot of different parties in a very complex industry. In the end goal of every party in the industry is at the end user sides. That's why they are a little bit in a different color. That's where the plants are. That's where the operation or the treatment happens. We directly work with end users a lot. You have seen a lot of examples in previous webinars. In this case, it was hybrid, let's say. But there, of course, we work at what we call 3E optimization: effluent, efficiency, emissions. CO2 is becoming very important. We are working on empowering the people as well, not only the process side, but also the people dimension. And also we develop a lot of digital twins with customers. However, this is now I'm going to come back to the other parties. We have a lot of big projects emerging, and there's a lot of things happening in the digital twin space as well. This word is mentioned 4 times on the slides, digital twin. So this also means in these frameworks, we really work together with big consortia. We are very complementary. For example, when you look at engineering and consultancy, AM Team is not an engineering firm. We are doing very specific work on enhancing, for example, de-risking projects, making projects very efficient. But we are not going to do plant engineering, for example, to a full extent. That's why we need these companies. We are also not a software company. There are plenty of good software companies in the markets. And we also do not develop technologies. We do not develop ozone technology, for example. But this is why we really work with all of these parties. And again, we want to fill this void in the markets. So you see the respective needs we try to fill with each party listed here on the slide without going into detail, okay? I just wanted to highlight this because it's important. If we want to work together, this is very important. How can we work together? Okay.